This is part 4 of a series on generative adversarial networks. In this video, we will look at Unrolled GAN. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the previous videos, we looked at 2 standard GAN models and used them to generate two-dimensional data and MNIST images with some success. We also observed the mode collapse phenomenon that occurs in standard GANs. Various GAN variants have been developed to improve the instability of standard GANs, such as mode collapse. In this video, we will look at one of them, the Unrolled GAN. Unrolled GAN was introduced in 2016 by Luke Metz et al. In their paper, Unrolled Generative Adversarial Networks. The authors of the paper introduce a method to stabilize generative adversarial networks by defining the generator objective with respect to an unrolled optimization of the discriminator. This illustration shows a computational graph for an unrolled GAN with 3 unrolling steps. The generator is updated by backpropagating the generator gradients through the unrolled optimization, indicated by the blue arrows. We will look at this in more detail later. Next, let's briefly compare the main differences between a standard GAN and an unrolled GAN. Let the parameter set of the discriminator be psi, and let the parameter set of the generator be phi. In a standard GAN, the discriminator is updated h times while keeping the generator fixed. H can be set to 1. And the generator is updated once while keeping the discriminator fixed. That is, the discriminator and generator are updated independently and alternately. If h is set to 2, this process can be represented as a computational graph as follows. Let the loss function of a standard GAN be g, a function of phi and psi. The initial parameter of the generator is phi0, and the initial parameter of the discriminator is psi0. Compute the loss g with phi0 and psi0 and update psi using gradient ascent. Then the discriminator parameter becomes psi1. Compute the loss g using phi0 and psi1, and then update psi once more using gradient ascent. Then the discriminator parameter becomes psi2. Then we compute the loss g with phi0 and psi2, and update the generator parameter phi once using gradient descent. By repeating this process, a standard GAN is trained. Next, let's look at Unrolled GAN. The discriminator is updated in the same way as a standard GAN. The generator is updated, taking into account how the discriminator reacts when the generator is updated. If the generator tries to generate an incorrect g of z, the discriminator will try to increase the loss. If the generator could know this in advance, it could try to generate a better g of z. This is the key point of Unrolled GAN. Unrolled GAN uses this surrogate loss function f to see the discriminator's response. F is computed via a kind of surrogate discriminator. This function uses theta instead of psi, which is the parameter of the real discriminator. That is, we introduce a surrogate discriminator whose parameter is theta and temporarily update it. In the paper, the parameters of both the real discriminator and the surrogate discriminator are denoted as theta d. but here we will denote them separately as psi and theta, which may seem a bit complicated. Set the initial parameter of the surrogate discriminator, theta 0, to the final parameter of the discriminator, psi 2. Compute the surrogate loss f with phi and theta 0, and update theta using gradient descent. Then the surrogate discriminator parameter becomes theta 1. Compute the surrogate loss f using phi and theta 1, and then update theta once more using gradient descent. Then the surrogate discriminator parameter becomes theta 2. Next, the generator parameter phi is updated as the surrogate loss f is backpropagated. This is similar to backpropagation through time in recurrent neural networks. This is an unrolled GAN consisting of 3 unrolling steps. In this unrolling step, the generator uses phi to generate g of z. Using this g of z, d of g of z is computed, and the surrogate loss f is computed. If g of z is incorrect, d of g z becomes smaller and f becomes larger. Then, the gradient of f with respect to phi becomes larger, so the generator updates a lot. That is, if g of z is incorrect, the generator will update phi a lot to generate g of z in a different way. This allows the generator to produce a better g of z. In the next iteration, the parameters of the discriminator are updated to psi 3, psi 4, and the surrogate discriminator performs the unrolling steps starting from psi 4. Note that during unrolling, the real discriminator psi is not updated, but the surrogate discriminator theta is temporarily updated. Next, let's look at how the generator of an unrolled GAN is updated mathematically. The GAN learning problem is to find the optimal parameters phi for a generator function g of z phi in the following minimax objective. Where g is commonly chosen to be as follows. First, we find the optimal psi star by maximizing g while keeping phi fixed. Then we find the optimal phi star by minimizing g of psi star. However, explicitly finding the optimal discriminator parameters, psi star of phi, for every update step of the generator g is computationally infeasible for a neural network-based discriminator. Therefore, this minimax optimization problem is typically solved by alternating gradient descent on phi and gradient ascent on psi. The optimal solution, phi star and psi star, is a fixed point found through these iterative learning dynamics. Additionally, if g of phi and psi is convex in phi and concave in psi, then alternating gradient descent or ascent trust region updates are guaranteed to converge to the fixed point under certain additional weak assumptions. However, in practice, g of phi and psi is typically very far from convex in phi and concave in psi, and updates are not constrained in an appropriate way. As a result, GAN training suffers from problems such as mode collapse and undamped oscillations. In order to address these difficulties, the authors of the paper introduced a surrogate objective function f of phi and theta for training the generator, which more closely resembles the true generator objective g of phi and psi star. F is a function of phi and theta k. The initial theta is psi, which is the parameter of the real discriminator. Theta k means that the theta is updated k times. If k is 0, theta 0 is psi, so F becomes G, which is the loss of a standard GAN. Next, let's look at how the parameters of the generator are mathematically updated using the surrogate loss F. The generator is updated via gradient descent as follows. Here we use the total derivative of F with respect to phi. Let's take a quick look at the total derivative. Suppose we have a dependent variable z that is a function of x and y. In most instances, x and y are independent of each other. They are not functionally related in most cases. But there are certain situations where y will be a function of x. So suppose we have this. Z is a function of x and y is also a function of x. Let's take the total derivative of z with respect to x dz dx. Dz dx can be found as follows. This is just 1. The first term right here is referred to as the direct effect. Clearly, it's the direct effect of x on z holding y constant. It's just the partial derivative. The second term here is the indirect effect. This is the indirect effect of x on z. It is the effect of x on y multiplied by the effect of y on z. In our case, f is a function of phi and theta k, and theta k is a function of phi. Therefore, the total derivative of f with respect to phi can be written as follows. Standard GAN training corresponds exactly to updating the generator parameters using only the first term in this gradient. Theta k is the parameter resulting from the discriminator update step. The second term captures how the discriminator would react to a change in the generator. This component represents the change in theta k with respect to the change in phi. It reduces the tendency of the generator to engage in mode collapse. For instance, the second term reflects that as the generator collapses to a particular mode of the data distribution, the discriminator reacts and assigns lower probability to that state, increasing the generator loss. It therefore discourages the generator from collapsing and may improve stability. As k becomes infinitely large, theta k goes to a local optimum of f, where the partial derivative f with respect to theta k becomes 0. Therefore, the second term in this equation goes to 0. Then this becomes equivalent to a standard GAN with infinite h. That is, it becomes a standard GAN, both when k is 0 and when k is infinity. Between these two extremes, the surrogate loss F captures additional information about the response of the discriminator to changes in the generator. The discriminator is updated via gradient descent using the loss G in exactly the same way as a standard GAN. Finally, let's look at the backpropagation of unrolled GAN. During unrolling, the generator is updated as follows. The gradients of F are backpropagated throughout the 3 unrolling steps. This is very similar to how recurrent neural networks are unfolded in time and how gradients are backpropagated through time. As we saw on the previous page, the total gradient of F with respect to phi can be written as follows. Here, theta 2 is a function of phi and theta 1. So the total derivative of theta 2 with respect to phi can be written as follows. Since theta 1 is a function of phi and theta 0, the total derivative of theta 1 with respect to phi can also be written as follows. Theta 0 is psi, which is independent of phi, so this term is 0. Rearranging this equation, we get the following expression. The first term is the gradient of the final unrolling step. And the second term is the gradient of f, which is backpropagated along the blue line. Finally, the third term is the gradient of f, which is backpropagated along the red line. Since we have 3 unrolling steps, the generator accumulates 3 gradients in total, 1 for each step. So far, we have looked at the learning mechanism of an unrolled GAN model. In the next video, we will look at 3 different configurations for implementing an unrolled GAN and implement an unrolled GAN and an unrolled DC GAN to see if they improve the mode collapse phenomenon.